combining optimal control and learning for visual navigation in novel environments. In this work, we focus on autonomous ground navigation in novel indoor environments using monocular RGB images. The robot starts at an initial position shown in blue and is tasked with navigating towards a metrically specified goal region, shown in green. For convenience, we visualize a top view of the robot's trajectory with free space shown in light gray and occupied space shown in dark gray. A projection of the robot's field of view onto the ground is shown in light blue. Note that the robot only sees first-person RGB images and does not have access to this top view. Our goal is to provide a framework for using model-based control for visual navigation in previously unseen, partially observed indoor environments. We propose a factorized approach which combines a learning-based perception module with a model-based controller. The perception module is trained to produce a waypoint which guides the robot toward the goal position while avoiding collision. Given a waypoint, the model-based planning module plans a smooth, dynamically feasible trajectory which it executes on the robot for H steps using robust feedback controllers. The entire process is repeated iteratively until the robot reaches the goal region. We now replay the previous robot trajectory, showing waypoints in magenta to help illustrate our method in action. We compare our method in simulation against an end-to-end method trained to regress from images to velocity commands, which are then directly applied on the physical system. First, we compare the success rate of both methods on a held-out set of 100 navigational goals in a previously unseen test environment. Our method outperforms the end-to-end method by roughly 25% on this held-out test set. To be fair to both methods, we compute the remaining metrics on the subset of held-out goals on which both methods succeed. The second metric we compute is the average time taken by each method to reach the goal. We find that the model-based method is 1.5 to 2 times more efficient in reaching the goal than the end-to-end method. Finally, we look at the average acceleration and jerk along the robot's trajectories for both methods. The model-based method produces substantially smoother control profiles than the end-to-end method. Smoother control profiles are useful as they are easier to track on a real physical system. Additionally, non-smooth control profiles could cause potential hardware damage and would certainly lead to increased power usage and decreased battery life. Through the training process, our agent is able to learn visual semantics of indoor office environments, such as exiting a room through a door, or navigating around a chair that may be only partially visible. We visualize one simulated navigational goal in which the agent must exit a room through a doorway to reach the goal region. The robot is able to learn that to exit the room it needs to first find a door and then exit through it. This behavior is learned even though the robot was never explicitly trained to do so. In addition to experiments in simulation, we deploy our algorithm on a Turtlebot 2 and test it in real navigational scenarios. Note that we train entirely in simulation and do not fine-tune our algorithm for these tests. These tests are shown in real time. We visualize each test from 3 different viewpoints. The first-person view is what the robot actually sees. The third-person view and top view are provided only for context. The first real-world experiment setting is similar to the experiment setting in the previous video. The robot is tasked with exiting the room through a door to reach the goal region. We demonstrate that our method is able to leverage the benefits of learned visual semantics and model-based control in a real-world setting. In our second experiment, the robot is tasked with navigating through a cluttered office hallway littered with bicycles, chairs, and sofas. Again, we demonstrate that the simulation-trained policy generalizes well to the real world. In our third experiment, we test the robot's response to dynamic obstacles. Given the reactive nature of our algorithm, we see that the robot is somewhat robust to moving obstacles. In this work, we present a factorized approach to autonomous ground robot navigation by combining a learned perception module with model-based control. We find that in a previously unseen, simulated environment, the model-based method reaches the goal more often and produces smoother, more efficient trajectories than a comparable end-to-end approach. Additionally, we demonstrate sim-to-real transfer of the model-based method in 3 real-world navigational scenarios.